All right, I've got the recording going. We're trying this one. So I'll steal this part and I'll ask you, first of all, we're doing absolute convergence first, okay? That's what we want to do. So for this guy, can he be negative right now for values, certain values of n? Or is he always positive? Is the sign always positive, Kelly?
No.
No. So when you're checking absolute convergence, you need to keep the bars on the sign this time around, okay? You need to keep them there. So again, if we're checking absolute convergence then of this, let's answer the questions. Is it raised to some weird power of n?
No.
Is it a piece series?
Yes.
Is it? Because a piece series, again, is of the form 1 over n to some power p.
Oh, no.
Maybe the 4 threw you off here. It needs to be n to some power, not a constant to some power. Okay, so it's not a piece series. Is the limit as n goes to infinity easy to find? So let's think about that. Does the limit even exist here? It does. You can use the squeeze theorem here, and you will find, if you use the squeeze theorem, you know, limit as n goes to infinity of 1 over 4 to the n on one side. In the middle, you'll have the limit that you're looking for. So sine of 4n here, absolute value over 4 to the n. And then that's going to be, again, less than or equal to this limit. There's a negative on the left there and a positive on the right. I'll explain where this came from in just a second. So it's because, again, over here, the sign right now, its value can only vary between 0 and 1 because you've taken the absolute value of this thing, okay? Sign goes like this. You've taken the absolute value of this thing, which means it's going to go like this right now. And so it can only vary, as you can see here, between 0 and 1. So you started off over here by basically putting in, let me keep this on the side here. Okay, so you started all off by claiming right now that the sign of 4n over here varies between 0 and 1. And then you multiply both sides by 1 over 4n right now. 1 over 4n, though, multiplied by 0 here gives you 0. 1 times 4 over n here keeps you the 1 over 4n. In the middle part, when you multiply it with 1 over 4n, the 1 over 4n, you know, the 4n goes in the denominator. So you have this situation here. And again, you're trying to take the limit as n goes to infinity. 0 here remains 0. This guy, though, when you take the limit as n goes to infinity, what is it, Kelly?
0.
0. So by the squeeze theorem, you see we've squeezed the limit of this to be between 0 and 0. So the overall limit would be 0, okay? And, well, it's inconclusive, right? The divergence test is inconclusive. We spent a little bit of time to look at it because it could have been the case, but we see that it is inconclusive right now. Because, again, we did the limit and we found 0. So we got to keep on moving to the right. Okay, so is it a product of factorials or brackets raised to the power of n?
Yeah.
Which one?
1 over 4n.
Okay, this guy, though, he's, when we say brackets, maybe I should elaborate a little bit. It's like 5 plus n to the n over like 6 plus 1 to the 2n. That type of deal is what we're referring to here. Do we have this kind of deal?
No.
No. Okay. So we keep on moving. Is it integrable? Is this thing easily integrable?
Maybe.
Well, you have a sine function over 4n right now, 4 to the n rather, okay? And if you use the u sub here, for example, or you replace this, again, you can't work this out with a u sub. You can try and see, you're not going to get, you don't have the derivative of any function in here so that the u sub can help. I don't see it. I don't see an easy way around this. Maybe integration by parts twice, maybe. And that's a maybe. So I really don't see a way around this other than that. So maybe, like you said. So we proceed to the right. What's your hunch about this?
Diverges.
Diverges. What do you base that off? I want to hear like your reasoning a little bit.
Because the n will go to infinity and then like it's keep going smaller and smaller.
Okay. Doesn't that mean though that we're going to keep adding terms that become progressively smaller and go towards zero? What's the largest term you're going to add here? Like take a look, right? What's the largest term you're going to add here? Think. For what value of n?
0.
0. I think the series started at 0. Let me just check to make sure. It starts at 1. Okay, that's okay. We'll correct that. So for n equals 1, what are you going to get here for, let's call this guy, I guess, here, a sub n. What are you going to get for a sub n right now for n equals 1?
Sine 4 over 4.
Sine 4, okay, over 4. All right, and that again, I'll do on the calculator real quick so that you know what it is. Sine, again, we're in radians when we do that, so make sure you're in that. Sine 4 over 4, and the absolute value of that is 0.189. Okay, so that's n equals 1 right now. What about, again, let me line them up like this because I hate this kind of table. What if you try 2?
Sine of 8 over 16.
Okay, 4 to the exponent 2. All right, so we get around 0.062, a lot smaller than the original term. And you can keep doing this and you can convince yourself that this series is dying. Okay, like it's the terms that we're adding, they're becoming progressively smaller. And I'm noticing here, Kelly, as well, that the largest term I added here was less than 1. So like, and this is progressively becoming smaller very, very fast. Like if you do the 3 right now, you get here sine of 12. Okay, which is a negative, of course. We'll make it positive because we're taking the absolute value. And when we divide by 4 cubed, we get here like very, very quick convergence. Look at this. Again, it doesn't mean that the series converges if the individual terms converge, right? If they reach, again, 0. But I'm looking at it here and just eyeballing it, how fast this thing dies to 0. And the fact that the largest term that we added was a very small number, my hunch here is that this converges actually. Okay, if I looked at these numbers. So if it is converging, we need something here to compare it against that is bigger than this, potentially bigger than this. Something that is consistently bigger than this. We're doing a comparison test if you want to know where we are. We're saying converges. Can you come up with a Bn that is larger consistently than a sub n? What are we thinking here? I will give you a minute as I'm writing here for you to come up with something.
Can you do like 1/4 to the n?
Okay, let's try that one. 1/4 to the n, you're saying. So if n is equal to 1, okay, that is just going to be 0.25 over here. Right, just 1/4 basically. And that's bigger. When n is equal to 2, that's going to be 1/16, or again, 0.0625. Still bigger. Okay. When n is equal to 3, 1 over here 4 cubed. 0.0156. Do you see that we're consistently bigger? You made a good choice. I will argue here that this continues on forever. We can see it because the largest value that sine approaches is 1. So this one that you have here, that's the largest value that this approaches. So the series that you wrote here is consistently larger or equal to the original. The maximum that this guy can become is equal to that, and only at very specific values for n, very specific values. So you have a series 1/4 to the n. Does this series remind you of something like the 1/4 to the n that you picked? What kind of series is that? Any idea?
Power series?
Yeah, it is a power series, and specifically it is a geometric series. Again, like the one we had last time, similar. And the thing is, the A value that would be sitting here is equal to 1, and the magnitude of the R value, which is this guy, the magnitude of the R value is equal to 1/4, which is less than 1, and that means that we converge by, I guess, geometric series test. Okay, and automatically for this one, because again, it's always smaller than the one that you have picked, okay? It's always smaller here, or equal, it doesn't matter, but it's always smaller than this one. We can combine these two facts to say the original absolutely converges. And what test did we use? The comparison test. Okay. There we go. No need to do anything else. You've reached here in the flow chart. You came up with a BN that's larger. And we saw that the BN converges. Therefore, absolute convergent. Done. So that's what we did here. We'll take the work downstairs. All right, so this was F. Does this make sense? We reached again the steps for the comparison test. You came up with a series that is larger consistently. We proved that the larger series converges, and therefore the smaller series will also converge.
Yeah.
All good?
Yeah.
Keep going.
H.
H. Okay. So this one says series from n equals 1 to infinity, 3 to the 1 over n cubed. Okay. All right, let's put it down. Actually, let's start from here just immediately. Let's go up here. Okay, I want you to think, if we're going to check for absolute convergence first, I want you to think if there is a way that we can get a negative number out of this. What do you think?
We will, because the denominator is the power to it's the cube. So
Okay. Well, your
when you-
numbers here,
when
Kelly,
you-
go from 1 to infinity.
Hmm,
You never put in a negative number for n in the first place. Could you get a negative here?
no.
No, because the numbers, again, if you put anything between 1 to infinity into the positions of n, you'll always get a positive here. So we don't need the absolute values. By the way, this means that right now we're checking for conditional and absolute convergence at the same time. So it's going to be a one-shot deal, okay? So if we end up succeeding in a convergence test, it means that we absolutely converge immediately. If we end up failing in a convergence test, it means right now we diverge immediately. We don't need to check the unabsolute valued function because we didn't really take an absolute value here. Okay, do we have the entire inside of this raised to some weird power of n?
No.
No. Is it a p-series? Close, right? But it has this thing. So we will say no again. It's not a p-series, really. Okay. Is the limit easy to evaluate? Now, I'll tell you here that it is kind of easy because you take the limit as n goes to infinity and you plug in infinity right now, you're going to get 0 up top over infinity in the bottom. And that's an inappropriate form. You can go in and for that kind of inappropriate form, I don't think L'Hopital's rule is useful. Okay, but here's the thing. This goes to 0, right? The numerator here goes to 0 when we plug in n goes to infinity, because that exponent right now, think about it. Let's think about it one sec. 3 to the 1 over infinity, okay? This means that we're basically raising 3 to the power of 0, correct?
Yeah.
Okay. The denominator, though, goes to infinity. So you have a constant over infinity. What does that go to?
1 over infinity.
Which is?
0.
So we did the limit and we got 0 again. So inconclusive divergence test. We move on. Okay, it's not the divergence test. You got to keep going. So is it a product of factorials or these brackets again of n?
No.
No. Is it easily integrable?
Maybe.
Maybe. Again, I don't see any u sub that could work here. If you plug in 1 over n as the u sub right now, you're going to get 1 over n squared from the derivative. So you're going to be left with 1 residual power of n in the denominator that you will have to replace in terms of u. It will get messy, okay? U sub might not work. So it's another one of those cases where, you might have to do integration by parts and pray that it works out. So maybe, and I would say probably not. Okay, so we're here again. What's your hunch about this? What do you think? You want to do some numbers first to see?
Yeah.
Okay. So let's put again a sub n over here. It is 3 to the 1 over n cubed. And then for n equals 1, what do we get here? We get 3 over 3. So just 1. Then for n equals 2, okay, we get square root of 3 over 2 cubed, or 8.
Wait, when n equals to 1, isn't it equals to 3?
So when n equals to 1, we get here 3 to the 1 over 1. You're right. I forgot the 3 even existed. Thank you for catching that. There we go. So that's exactly 3 right now. And then the other one over here, when n is equal to 2, it's 3 square rooted.
Yeah. So 0.2165.
Yeah, that's the number. Let me just do it on mine so I can copy it. So it's converging pretty fast. 0.2165, let's say. And then let's do another one. So for 3 over here, we get 3 to the 1/3 over 3 cubed. So we get 3 again to raise to the power of 1 over 3, and then divided by 27. You get here 0.0534. My hunch again, considering what the first number is, the largest value that we're going to have in the sum, my hunch is that it will converge. It seems to be, again, the terms seem to be dying pretty fast. Like if I started like this, if I had like 100,000, or 1 times 10 to the 5, and then the next term here was like 9.99 times 10 to the 4, and then the next term was like 9.999 times 10 to the 4 again. Like this kind of thing is slowing down, but it's slowing down very slowly. Here you see you've dropped like several orders of magnitude each step. You've dropped like a factor of 10 here, and then another factor of 10 here. Every one n that you're moving forwards, it's like dividing by 10 the answer that you get here. That's a very fast convergence. So if you were only slicing it by 2, for example, I would be more concerned. But you're slicing it by 10 or more over here every time you go forward. So that's pretty fast. My hunch, therefore, is that, again, this thing converges. Okay? And so I would go and find right now a series that is larger than this. Let's think about this. A series that is consistently larger. Keep the n cubed around because we can't do much with that right now. But with the top over here, I see that pay close attention here. I see that the largest value that the top can be ever during this series is what?
3.
So if we picked 3 here, there's no way we would ever be less than the left over there. We could match it, but we will never be less. Let me show you again. If you pick this as your Bn right now. So for n equals 1, we'd get here 3. So that's exactly equal. But that's okay. We need to be, again, larger or equal. So we don't want it to be the same, of course. We don't want it to be the same series because that's meaningless. I guess we can say that would be inconclusive if we literally compared a series against another one that is exactly doing the same thing. I don't think that can even happen anyways. But the first term here is the same for both of them. They start off the same. Then immediately, as you go to the next value, you get 3 over 8, which is 0.375. and that's larger. And then for the number 3, you get 3 over 27, which is 0.111 repeating, which is again larger. You can keep going. If you don't believe me, all of the other ones are going to be larger as well. So you got over here a series that is greater than or equal to the original. Okay, all right. So if this larger series converges, then so will this one. Otherwise, we will be inconclusive. What is this? Think about it. I'm helping you out a little bit.
Geometric series.
Close. Close. It's another one that we are always asking in the beginning about.
Power series. P series.
P series. Okay. It's a P series. Okay. P here is equal to 3. So it's more than 1. Okay. Therefore, converges by P series test. So the exponent on the denominator is greater than 1, which is all that we're looking for a P series. So it converges by the P series test. And therefore, this one, which is consistently smaller or equal to the one that we just analyzed, will also converge by the comparison test, though. So original.
Wait, sorry, what's the difference between
Yep.
this P series with the geometric series?
The fact that in the geometric series, we have a number raised to some power here. And in the P series, we have n raised to some power.
Oh, okay.
Okay, so it's this time it's the n raised to some power. Similar creatures, but quite different. Okay, so when we have this situation, now we know, since you picked one that is consistently larger and you found that it converges, then the smaller one obviously will converge as well. So we have original absolutely converges by comparison test again. There we have it. So we stopped again at the comparison test. Seems okay?
Yeah.
That's how I recommend going about the comparison test, right? I want you to look at a few of the terms, see how fast this thing converges, kind of judge it by eye and be like, make a conclusion. And you could get it wrong. It's okay. You might get a hunch here that this should be diverging. Okay, and if you get that hunch, you go over here, okay? And if you fail it, that means it must be converging. And if you can't find a BN, again, that you can do this test on, you move on to the next step. But again, don't be disappointed if you get the wrong thing. It actually will happen. When you're doing the comparison test, you might get the wrong hunch, therefore start trying to prove that it diverges, and then you'll realize that it doesn't, right? And then you'll go back to try to prove that it converges. It's okay. It happens. But the terms certainly help, keep in perspective if this is going to converge or not. Okay. So let me just put that here, just fix the presentation of the answer. That was H, right? I think that was H. All right. Another comparison test. And I like that these are nice and short. We don't have to do a, alternating series test. Keep moving.
I.
Okay, this one looks pretty nasty. I don't like the arctan. Okay, so tan inverse of n over n. I really sense here this is another comparison test. I really do. But how am I going to prove that? Well, we'll see. Put it here and bring this upstairs. Okay, so we're going to check again absolute convergence first. So could this get you a negative right now? Could it? Do we remember what this even looks like? This is probably a good point here to remember what this function looks like. Okay, so the regular tangent, I'll put that on the work that we have for the problem. The regular tangent, it has asymptotes. So again, we can fit them here, those asymptotes between negative pi over 2, positive pi over 2, and the tangent goes like this and flirts with them. Okay, and then it repeats, the pattern here repeats, like you'll start again over here, which is like pi right now, and then you'll have another asymptote over here, 3 pi over 2, and then the function will do this again. Okay, so this is how the tangent looks like. Both sides again look like this. If you go to the negative side, it looks the same. Now, if we want to define tan inverse, okay, we can't pick the entire function because it will fail the vertical line test. So we only got to pick something that doesn't repeat here. Because again, if you invert this right now, you're going to get something like this. Hold on. It would look again, yeah, something like this. The curves would look something like this. I can't draw them really, but they would fail the vertical line test if you took all of them and inverted them. So why not invert one of them? Because that will not fail the vertical line test when we take the inverse. Okay, so why not take this branch over here? Okay, and what we're going to do is we're going to invert it. Inverting it is like a reflection right now. I'll show you. So inverting this is like reflecting it about the line y equals x, if I remember correctly. Let me just think about it for a sec. I think that's correct what I said. So it's like a reflection. But really, if you want to see it better, the inverse of this right now, Kelly, it will be, think of it as you looking at the function from this direction right now. Okay? Your eyes are looking at it from this direction. So what would you see? Turn your perspective again to that direction. You would see something like this. Again, hold on, let me make sure I don't screw this up. So we have a negative pi over 2. Yeah, so it's going to look something like this. And again, the values, here they go. So this one's going to be the positive pi over 2. That one's going to be the negative pi over 2. I'll put them side by side so you can see them. Yeah, I just want to draw it in first. All right. There's the asymptotes again, how you would see them. So let me be really careful. Yes, that looks about right. And then we have 0 being the point right there. It's mutual between the two plots. So you approach negative pi over 2, you go to infinity. Positive infinity. Yep, and that's what's happening here. You go to positive infinity when you approach negative pi over 2. Okay,
So
hold on. I
when
think I've got it. I think I've got it actually inverted. Hold on. I think I've got it the wrong way here. So when you're going to negative infinity, you're approaching negative pi over 2. And negative pi over 2 is here. Sorry, the lines here fooled me. I thought this was positive. Okay, so at negative infinity, for our x approaches negative pi over 2. So it looks actually like this. There we go. So negative infinity, negative pi over 2. And then the other one, positive infinity, positive pi over 2. That's what's happening there. There's our inverse. Okay. So as you can see, it's bound. Okay. Let me bring these plots down here. We're going to do a little bit of work on the tangent to understand the tangent inverse first. Okay. All right. So can only invert pink part. Okay. So that's what we did. There is the inverse. And I want to ask you now a couple of things about its domain and range. Obviously, the domain here, Kelly, is unrestricted, like negative infinity to infinity. You don't have a restriction, but you have a restriction on the range. What is that?
between negative pi over 2 to positive pi over 2.
Exactly. Keep that in mind. So now, if we're going to check for absolute convergence first, okay, is there a chance that this gives us a negative number? Look at the plot again and the range.
No, because we start from 0 to infinity.
Good. I'm happy you actually observed that. It's a 1, but you're very good. That's hard to catch. So think of this as being your term axis over here, and this being your n right now. You're starting the series. Hopefully, I catch this well in the recording. You're starting the series at n equals 1, which means you're somewhere over here. And that means now you're always going to be positive forever. Forever. Of course, you have an upper window you can reach. You can reach pi over 2, but your lower window right now is not negative. So when we take the absolute value of this, we don't need the bars because, again, we're always going to be positive from 1 to infinity. That's the thing. And that's why it's so important paying attention to these ends over here, where they start from and where they go. Because now I know, yes, tan inverse can give you negative numbers, obviously, the whole branch here. But my series uses the tan inverse from 1 onwards. So I don't have to worry about that. I never touch negatives on that function. And so, again, taking the absolute value just yields the same thing. Now we're good to go. So, okay. Then for n again, let's think about this. For n, between 1 and infinity, what is the range for the tangent? So the smallest value that we can be right now, Kelly, is this, like this guy over here, which is going to be tan inverse of 1. Do you know what this is as an angle off by heart?
45 degrees.
That's a special triangle, the one that has opposite and adjacent sides equal. Okay. So domain, rather range, excuse me, range of tan inverse n is equal to pi over 4. And again, if you plug in infinity, where are we at infinity again? If I go all the way out here.
Pi over 2.
Exactly. Those are the values that the tan inverse can touch. All right. We got what we needed. Let me ask you the questionnaire here so that you see again which test I'm going for, but you probably can see. Is it raised to some weird power of n, the whole thing?
No.
No. Is it a P series? No way.
No.
You see that? I know you see the 1 over n, but you see that. That already tells you it's not a P series immediately. Is the limit easy to find? Kind of. Kind of. I mean, tan inverse again is bound between negative pi over 2, the range again that it can give, and pi over 2. So you can use the squeeze theorem again here, okay? Negative pi, I'm just going to show you for curiosity's sake. And then what you're going to do is multiply the rest of it in here. So take the limit as n goes to infinity. We have negative pi over 2, and then we put in the 1 over n bit. So we can use the squeeze theorem on this bad boy. So tan inverse again n divided by, again, this. And we've bound that between this and the right-hand side, which is pi over 2, limit as n goes to infinity of 1 over n. What are these limits here, Kelly? This one, and again,
it will goes to 0.
so the limit of this one is squeezed to be what?
0.
And is that conclusive or not?
It's conclusive.
Okay. If we get 0, we got to keep on moving. Divergence test failed. Anyways, I just did it so I can show you the squeeze theorem a couple of times because you might forget it. Is it the product of bracket? No. Okay. No factorials. Is it easily integrable? I'd say absolutely not. Like, I'm only thinking of the nightmare of integrating this and finding a good substitution for it. What could we even use, right? Tan inverse. You know, tan inverse, if we integrate it, no, I don't know that explicitly. I don't know that antiderivative. So even if I use integration by parts, I'd have to differentiate this, integrate this, and again, it might not work out. This is going to be a long integral, if anything. There is something I can do, but it's probably not even going to work. So I'm going to go with maybe no. What is your hunch about it? Here's where you're starting to do the terms. Okay, seems like it's going to be another comparison test to me. So an is tan inverse of n over n. Okay, we got here. We're going to try a few of these values to see what we get. If you try these in your calculator, make sure you're in radians when you're doing this. Okay, so n equals 1. Top is going to be pi over 4. Bottom is going to be 1. So you get pi over 4. Or again, I want it to be an exact number because we're going to compare it to another series. Pi over 4 is 0.785. N equals 2. Tangent inverse of 2 divided by 2 is 0.554. Tangent inverse of 3. Okay. Divided by 3. 0.416. Okay. And Do you see how slowly this is converging?
Yeah.
That's a bad sign, okay? And I want to convince myself that I'm not going crazy. So what I'm going to do here as an extra point, I'm going to do n is equal to 1 times 10 to the 6. Okay. Tan inverse of 1 exponent 6 divided by 1 exponent 6. I mean, it's a small number, but it's still nowhere close to 0. 1, 2, 3, 4, 5, 6. Okay. So the problem here is I'm noticing that it's slowly converging. So I can't tell you with certainty. I'm thinking here, I'm thinking it could do both, because this is a borderline on my judgment here, if it would converge or if it would diverge. Okay. Now, here's the thing. Okay, here's the thing. We don't know. And I love this example because I want to show you what happens when you're not sure. I'm kind of iffy. It could both diverge and converge. So it means I have to make a choice here of what I'm going to set myself to prove. Just like in linear algebra, you're going to set yourself to prove something. And if it fails, you're going to try and prove the opposite. What would you like to try and prove here? That it converges or diverges? What do you think?
Hey, can you repeat that again?
So what do you want to try and do here? Prove that it diverges or converges, because it's 50-50.
I'm not too sure.
Okay, I'll pick for you. I'm gonna choose to see if it diverges. Okay. Again, my hunch here, it's very slow. I would go with trying to prove that it diverges. So I gotta pick a series here that is consistently bigger. Yes, no, the other way. My brain had a brain fart there. It is consistently smaller, and again over here diverges. That's what we want to do. Consistently smaller, but diverges. Here's where our information on tan inverse is golden. We said that tan inverse can vary between pi over 4 and pi over 2. So right now, if you pick a number, literally any number that is actually smaller than pi over 4, you've won. Pick a number that's smaller than pi over 4. Let's see here. Pi over 4 is like
Pi over 8.
Pi over 8. 1/2. 1/2. Why not 1/2? Replace the tan inverse with 1/2. And then the denominator, leave it the same. So that you get here 1 over 2n. Let's see if I'm right. Again, if this is always consistently smaller. Okay. 1, if n is equal to 1, we get here 0.5. If n is equal to 2, we get 0.25. If n is equal to 3, I have to do that on the calculator. 0.167. If n is equal to 1 times 10 to the 6, we get 5 times 10, 1, 2, 3, 4, 5, 6, 7. Do you see what I'm talking about? Always smaller. Now you should get strong vibes here on what Bn is and what it will do. So what kind of series is this that I have in my hands?
Um, 1 over n is the
Mhm.
geometric series.
The other one.
Oh, a p series.
And what is the exponent on n?
1.
Okay, that's a problem. That means we diverge. Diverges by p-series test. Okay, so you did what you set out to do. And now, again, over here, I'll write my conclusion that this is consistently bigger than the right one, but the right one was found to diverge. Therefore, the left one will also be diverging. So again, what we do here is we were checking for absolute convergence, right? But here's the thing. Hold on, look at the chart. It will tell you the truth, what you need to do next. You come up with a Bn that is smaller. Yes, 1 over 2n. Okay. Does your Bn diverge? Yes, it does. Was the original series alternating?
No.
No. There's your answer. So we don't have to go and check for conditional, okay, because we're not alternating. So we are, again, diverging by comparison test. All right. And that's it. So I'll put the work here for this one underneath the work that you've done for the rest. You see, it's good to know how the tan inverse works as a function, because once we did that, we basically knew what to do when we arrived at the, test, at the comparison test. So I'll put that here. All right, I think we are good. So that's it. That's your work. You got to understand what the tan inverse does, where it varies between. You see, it was so important to get this, okay? Because now you know that in order to find a series that's consistently smaller, all you need to do is replace the tan inverse with a number that's to the left of pi over 4 here. That we chose 1/2. Okay, it could have been 1/4, anything, 1/5. But something that is smaller than pi over 4 will consistently give you a smaller series. And that's how we did it. So it doesn't matter if you pick that to be 1/2, 1/4, 1/6, 1/24. It doesn't matter because this is a constant and this still be a series that diverges. How are you doing, Kelly?
I think I understand it now. Yeah, I think I would try doing some myself.
All right. Is there any one of them that you want to do here now?
No, I think I'm good for now.
Okay. Have I shown you some of the weirder tests? Wait.
Yeah,
This one,
you showed me K as well before.
I've shown you K. Okay. Now
Yeah.
this one here, my hunch, before I even look at the chart, that's going to be a ratio test, I think, because I see factorials. When I see factorials, that ratio test comes in clutch. I could be wrong, but that's again my hunch. The rest of them, that smells like a comparison test again over here. I'm not sure about the other ones. We'd have to look at a little bit and think about them. But yeah, you can try them if you want. Okay.
Okay.
All right. So for the last bit then, let me show you Newton's method, because that's on your test, and the intermediate value theorem and all that stuff. Do you remember what the intermediate value theorem says?
No.
Okay, good time to review. So basically, if we have a function that has a root right now, okay, right there, and I suspect that there is a root between two x values. Let's say here, the x values I suspect are here, x left, and x right. Notice that if I evaluate the function at the x left right now, I'm going to get a positive, am I not?
Yeah.
What happens if I evaluate it here?
Negative.
Absolutely. So I'm just going to write here f of x right is less than 0 and extend the axis. So again, here's the intermediate value theorem. Okay, there exists a root between two x values if the value of f of x is different signs when evaluated at those x's. Okay, that is it. So what you want to do here is check to see if you have a polarity flip between the range that you suspect you have a root. Because if your function flips polarity, so if you had a positive here at the x left, like here, how can you get here without crossing the x-axis? How can you do that? You have to cross somehow, I don't know how, but you have to cross the x-axis. You have to. So that means there has to be some root in this area here. There has to be a point where you traverse through the x-axis and make it to the other point that's in the negative y-axis, right? There's no other way. It's like saying, in my room, there's like wall everywhere, right? And I have to get from this room to the one adjacent next to me. There has to be a door somewhere. How am I going to do it? Am I going to teleport? Right? You can think of it as you being in a room here, and the room next to you. Here's the room. Let me explain this in terms of rooms. That's room 1. Okay, and that's room 2. Okay, so if you're in room 1 right now, you gotta have a door somewhere. You gotta have a door somewhere over here. Okay, if later on you're found in room 2, you have to have some kind of door here that you actually went through. I don't know how you went through, what function you were following, but you have to pass through some door. And that door is the root. It's an analogy for the root, basically. Okay, Kelly. So that's the idea. You can think of it in rooms. You can think of it, again, that you just have to have somewhere a crossing, a bridge between those two, the positive y-axis and the negative. So you have to cross the x-axis. So all that we have to do to prove there's a root between two x's is prove that the function has different signs at each of those x's. Our function here in this example is f of x equals to x squared minus ln x plus 3. And we're suspecting root where? Between, see what it says? Between 1 and 2. Between 1 x2. Okay. So what do you think I'm going to do here to show that there is one? What is the goal? You have it?
No.
Okay. I'm going to evaluate the function at 1 and then at 2. Let's see what happens. You got 1 squared minus ln of 1 plus 3. On the bottom, you got 2 squared minus ln of 2 plus 3. Okay, so top one, 1 minus ln of 4 is negative 0.386. And then the other one is 4 minus ln of 5, and that is 2.39. You see what's going on? You have opposite signs for the function. So basically, in the form of a plot, what has happened here, you've looked at 1 and you've looked at 2, and at 1, you were at a negative value somewhere down here. I don't know exactly where. Hold on, let me make it symmetric. Okay. And that one gave you here negative 0.386. So you are here. And then at 2, you got a positive. You got here positive 2.39. So you're out here. You see, you have to cross here. Okay, and you can cross it in many ways. You can cross like this. You can cross, I don't know, like this, like a parabola, right? You can cross, I don't know what the function looks like, but I know it's going to have a root there because we have to have crossed. You see, we jump from here to the other side. We can't teleport through here. There's no discontinuity here. You literally have to cross. You see how we prove it? Tell me if that makes sense, Kelly.
Yeah.
Okay, so I provide the plot. If I were you and I was being asked about the IVT, I'd provide the plot as a supplement because it really shows you understand what's going on. It shows, again, you know why there is a root in between the 1 and 2. Okay, so pick a number between 1 and 2.
1.5.
Okay. So choose over here x naught between, again, 1 and 2. That should be x1 rather. Okay. All right, and you chose here 1.5. That's fine. Do you remember how to apply Newton's method? Yeah, no?
No.
Okay. I sometimes forget where the derivative goes, if it goes on top or bottom of the ratio, but it's going to be, again, just going to risk writing it right now. It's going to be, for Newton's method specifically, that's not what I wanted to do. Okay. So the next guess for the root is going to be the previous guess minus the ratio of the function evaluated at xn divided by the derivative of that function evaluated at xn. But I usually mix the order of these, so I'm going to check to make sure that I didn't get it wrong. 50-50. Otherwise, I'd have to derive it. If I was really having a gun stuck to my head, I'd have to derive it. It's always, I'm forgetting this. So it was in 127 day 3. Yeah. Okay. So derivative is at the bottom. Good. Okay. Good. So we need here, we need our function. The part with the IVT is gone. Okay, this is like A. Or actually, this is A. This is just me talking about the IVT here. Hold on. Let me separate the parts. That's just part of the note. Okay, so this is A, proving that there exists a root between those two values, so we can get our Newton's method started. Okay, that's what we have. We need, again, derivative and function. The function is this. Can we differentiate it? And I hear you, Kelly, here differentiate this.
It will be 2x minus 1 over x plus 3 times 1.
Yes. Perfect. So you picked here 1.5 to start this off. That's going to be the first value that we try. All right. X1 is 1.5. So we need to try and find here f of x1 and f prime of x1 right now, which are going to be, if we plug the values in respectively, 1.5 squared minus ln of 4.5. You get minus 2.25. And then the derivative, 2 times 1.5. And then let me do that separately, 1 over 4.5. And then we have this minus this, 2.778. Okay, so the next guess for the root will be the first guess minus the function evaluated at x1 over the derivative evaluated at x1. And so we get, again, if you want to see it in numbers, 1.5 minus 2.25 divided by 2.778. There we go. So let's see it. 2.25 divided by 2.778 plus 1.5 is 2.31. Wait, really? What did I do here? What did I do wrong? What did I do wrong? Hold on. Probably screwed up something. Let me see.
Wait, sorry, I'm gonna go to the washroom. Give me 1 minute.
Yeah, I'll pause the recording. Go for it. So I did catch the error here. I literally forgot to subtract this part from the first guy. So he's 0.746. And then when we plug it all in together, we get the next guess at the root to be 1.23146, whatever. And then here, Kelly, the next guess to guess in iteration 2 is what we came out from iteration 1 with. Okay, so in the same process right now, we're going to evaluate the function and Newton's, again, the derivative here to put into Newton's method. So I want to carry these with me because I forget what they look like. Honestly, we can work a little bit on the derivative to make it look better. I'll cross multiply to get myself 2x, x plus 3 minus 1 over x plus 3. And this will be 2x squared plus 6 minus 1 over x plus 3. So we get 2x squared plus 5 over x plus 3. I think it's easier to work in the calculator if you write it like that. Okay. Anyhow, so moving that a little bit lower. There we go. So I'll take with me this instead of this mess. It's a little bit easier to work the numbers. Okay, so we want to work this to 6 decimals, they said, but I'm not going to do, I don't know if we're going to go all the way there. Might be 3 or 4 iterations before this happens. But again, if I plug in this number, 1.23146, let's store it in A right now so we can use it quickly, like store it in memory. 2 times this number squared. So I'm calculating the derivative first and divided by this number plus 3. Okay, so this is 1.898384 really. Okay, and then we have the other one being, again, 1.23 squared minus the logarithm of this number plus 3. Okay, that is, we're very close to the root, 0.0739. And so, get the next guess, we take the previous guess and subtract the function at the previous guess over the derivative at the previous guess. So 1.23146 minus 0.0739 over 1.8984. Okay. 1.8984 times -1 plus this number gets you x3 approximately 1.19251. All right, and you keep on going until you get agreement within the decimal places that they want you to. Now, Newton's method converges really, really fast, okay? So you'll see if I keep going in iteration 3, I'm basically gonna be at the root right now, okay? If I try continuing with this, just look how fast we're gonna converge. I'll keep this number in memory. Bring my functions down here, and I'll have, for the first one, for f of x3, I'll have 1.19251 squared minus ln of this number plus 3, negative 0.011222, okay? And the derivative at that same position is 2 times this number squared plus 5 divided by this number plus 3, 1.87099. So the next guess to the root is the previous minus the function at x3 evaluated by the derivative at x3, 1.19251 minus 0.01122 divided by 1.87099. Okay. All right, so I have minus 0.01122 divided by this times -1 plus the original number. You get x4 is approximately 1.198,507. And you will see now that we already agree to 3 digits, okay? If you do it again, I'm willing to bet you're either going to agree to 4 or 5 digits. And if you do it one last time, it's going to give you the 6 decimal accuracy that you want. But it converges really fast. It's way faster than the bisection method. And that's how it works. It's an iterative process. You can code it. You can make a piece of code to calculate this super fast like this. Okay. And that's how it goes. Is this straightforward, Kelly? Like the iteration?
Yeah. But like in our exam, we don't have like calculators. So do you think this topic will be on the exam?
If they gave it on the exam without a calculator, they will give you numbers for the function that are super easy to do. Like the function and its derivative would be like super simple. Think of it, there's not going to be a ln, first of all. It would be like f of x here equals to like, I don't know, like 3x, okay? Its derivative right now is always 3, right? So you can see here, if you guess the root of this to be near 0, let's say, I don't know, 1 over 10, you can kind of work these fractions into this without really causing a mess. And
Okay.
if they don't allow you to use calculators, they'll make sure that the numbers are doable as fractions by hand. Okay.
Okay.
Last but not least, okay, so let me see what remains here. So we've done most of the series convergence stuff. We worked on Taylor's series. I showed you Taylor's inequality. We worked on power series. What is it that I have not done? I see there's one more topic I haven't done on power series, and that is to derive, okay, power series from other power series. I don't know if we've done that. I don't think we have. So let me explain what I mean by that. Your power series is always based on, if I remember correctly, this guy. That is the building block for your power series. He goes from, again, 1 to infinity here, x to the n. This is the power series representation that you always start with. Okay. Let me show you again, Kelly.
Wait,
Yeah.
sorry. How long do you think this session will go? Because I still have a quiz that I haven't done, like finished yet. So I have to go
You
soon.
want me to cover it with the others?
Yeah, sure.
Okay, I'm thinking it would be like 20 to 30 minutes.
Okay, yeah, sure.
Okay, so I'll leave this to be covered then. How to create power series of other functions. Like if I give you right now, if I asked you, can you do the power series of this? Using this, we can convert, okay? We can find what the power series representation is for that. That is the goal, and they will ask you this. I'm willing to put my hand on fire. That's a hot topic. So, okay, we have one more session tomorrow where I want to cover then this and a little bit on big O notation, which even me, myself, gets confused by to this day. I never really settled with understanding what they mean by big O notation, but I'll try my best, as I usually do, to put it in perspective, okay?
Okay.
Last session then again, I know that it's coming up, your final. Last session's tomorrow, I'm pretty sure.
No, I think it's Thursday.
Thursday. Sorry,
Yeah.
Thursday.
Tomorrow is 106.
Yes. Thursday, I see here on my calendar at 8.
Yeah.
And that's it. So I'll see everybody for 119 then. And tomorrow we'll do EC 106 in the evening.
Okay.
All right, Kelly, one sec. Let me stop the recording here then.